Hi, welcome to my econometric tutorial and thank you for joining us. My name is Kamba AY. In this series 2 unit 1 of this video, we'll be looking at simple regression model. Don't forget to like, share and subscribe. Regression analysis generally is a statistical technique used in predicting the unknown value of a variable from a known value of another variable or set of variables. The variable whose value is unknown is the dependent variable and is usually denoted as y, is also known by other names such as the endogenous variable, the explained variable, the response variable, or the regressand. Then the second variable, the independent variable whose value is assumed to be fixed or known, is also known by other names. It's usually denoted as x and is known by other names such as the exogenous variable, the explanatory variable, or simply the regressand. Now, regression model, on the other hand, is a mathematical equation showing the relationship between x and y. The equations you find in 1, 2, and 3 are examples of regression model because they are equations showing the relationship between the dependent variable y and, of course, the independent variable x. Now, this regression model could be simple or multiple. It is simple if it has a single dependent variable and single independent variable, such as the one we have in equation 1, 2, and 3, and it is multiple if it has a single dependent variable but with a set of multitude of explanatory variables, perhaps noted as S1, S2, S3, and so on. Now, a simple regression model could be linear or non-linear. It's linear if it satisfies at least these three conditions. The first is that it has the highest power of 1. If you look at the model in 2 and 3, you see that y has the highest power of 1. That is, the power of y is not 2, 3, or half. It is just 1. Y means y raised to power 1. BO means BO raised to power 1. B1 means B1 raised to power 1. S also here means x raised to the power of 1. So, when y is raised to the power of 2 or raised to the power of half, then it makes the model a non-linear model. Then the second condition is that the graph of the relationship between x and y, when plotted, is expected to be a straight line. This is what we mean by that. Okay, if you look at this graph here, this is the y-axis, this is the x-axis, and of course this is the equation. You can say that this line is a straight line, okay, showing that there is a positive relationship between x and y. The line could also slope downward, okay, showing that there is a negative relationship between x and y. However, the fact that it is a straight line shows that the relationship between x and y is a linear relationship. Then the third condition says that the change in y resulting from change in x bears a constant ratio. What we are trying to say here is that, let me quickly demonstrate this using our Excel sheet. Look, we have two variables here, x and y, and you can see that the value of x is rising from 4 through 6 to 8 and then up to 16. So here x is changing by equal amount. That is, there is the difference of 2 for each successive between one observation and the next observation. If you look at y2, there is equal interval between the first, the second, the third in that order. That is, the change from 40 to 45 is the same as the change from 45 to 50, the same as from change from 50 to 55 in that order. So there is a difference of 5 between each of these observations. So now, if we look at the change, if we divide the change in y by the change in x for every data point, it's going to give us a constant ratio. For example, 40 to 45 will give us a difference of 5. 4 to 6 will give us a difference of 2. Now, 5 divided by 2 will be 2.5 at this point. If you come to this point, 50 minus 45 will give us 5. 8 minus 6 will give us 2. Then you have 5 divided by 2 at this point, it will still give us 2.5. So you have 2.5 as the change. So this is what we mean by constant ratio. Any value, or rather data set, that obeys this ratio, called eccentricity, is an indication that the relationship between the variables that generate this data is a linear relationship. Therefore, that equation is said to be a linear equation or a kind of linear simple regression model. So, to demonstrate that further, let's plot the graph of this relationship, and you will see that it's going to be a straight line rather than a curve. Okay, I go to insert, I go to where is the option? Okay, this is the option. I click and I plot. You can see that the relation, look at the y-axis, and of course look at the x-axis. So you can see that the relationship between x and y is a straight line and it slopes upward. So this shows that there is a linear relationship between x and y. Okay, now compare this to this other variable here. Okay, where is it? Where is it? Okay, yeah. Okay, here you can see that the ratio of change in y to the ratio of change in x is not constant. Okay, 13 minus 40 divided by 4 minus 2 cannot give you the same ratio as 47 minus 13 divided by 5 minus 4. So this one is expected to be a curve rather than a straight line. Let's try it. Okay, I go to insert and I come here and I click. You can see that it's a curve. Therefore, the relationship between x and y that's generating this data is not a linear relationship, and as such, that equation or model is said to be a non-linear model. Okay, now a simple regression model is specified in either of these three forms. Equation 1 is a functional relationship between x and y. That is, y here is the dependent variable, x the independent variable, f is a functional notation. This one is telling us that f is a kind of is mapping y into x, or in other words, x is a kind of function that relate y to x. Now, the major limitation of this relationship, this equation, is that it is not estimable. We cannot know the value, or rather the amount by which y is changing as a result of change in x. Therefore, leaving this equation in this form has a problem. It has to be restated in a way that will make it estimable. So that is why we have to re-specify the equation to make it look like what we have in equation 2. Now, the relationship between x and y here is very, very significant, in the sense that two parameters, bo and b1, are introduced in this model to make it estimable. We can, in other words, solve for the value of BO using statistical technique. We can solve for the value of B1 using statistical technique, and by so doing, we have estimated this model. However, this model is called mathematical model because it assumes that x is the only determinant of y, and that is one of the major limitations of equation 2. X cannot be the only determinant of y. For example, let us assume that y is quantity supply and x is price. There are other factors determining supply. Or if y is demand and x is price, then there are other factors such as price of other commodities, income of the consumer, and so on that could determine the behavior of y. Mathematical relationship does not specify that. Therefore, it is weak. Then we have to specify this equation to take into account, okay, this limitation by introducing the error term into the model, so that rather than having y equals to bo plus b1x, we now have in equation 3 y equals to bo plus b1x plus mu. So the equation you have in 3 is an econometric model, and of course the difference between equation 2 and equation 3 is the mu, or rather the error term introduced into the model. So what equation 3 is telling us, that apart from x that determines the behavior of y, there are other factors that determines the behavior of y that we do not know. They are very numerous, but all of them are summarized and captured into mu. So if y is demand and x is the price, demand for a commodity, and x is the price of that commodity, then mu capture other factors such as the income of the consumer, population, weather condition, government policy, and many other factors that determines the behavior of y. So that is why in econometrics model, we are interested in the error term, not even the parameter. Because the smaller the size of the error, then the better the model. We have confidence in whatever estimate we are able to arrive at after the model has been estimated. So error time is the significant factor in an econometric model. All right, so in this model, we have the variables, which are y and x, that is the dependent and independent variable. Then we also have parameters. BO and B1 are the parameters. So you can see BO is called the intercept parameter, B1 is the slope parameter, and of course mu is the error term. The intercept parameter is a constant term. It is the value of y when x does not depend, when y does not depend on x at all. That is, suppose x is 0 in this model, then y will be equals to BO. So BO is the value which y must assume suppose there is no noticeable relationship between x and y. So it is the intercept term, or rather the intercept parameter. Then B1 on the other hand is called the slope parameter, and of course it measures the change in y resulting from a unit change in x. If x changes by 1 unit, the amount by which y will change is denoted by, or is measured by, the slope parameter. We already explained what the error term is all about. Then, nonlinear model, on the other hand, is one in which the relationship between x and y is a curve when depicted in a diagram. We have demonstrated that earlier. So we said that is the power of either the dependent or the independent variable or both is greater or less than 1. So if look at y is equals to ax raised to power b plus mu, for example. If b is equals to 1, for example, then the model is a linear model. But if b assume any value other than 1, then the model becomes a nonlinear model. So, for example, if b is equals to 2, it's a nonlinear model, and that nonlinear model is a quadratic model. If b is equals to 3, it's a nonlinear model, and the model is a cubic model. If b is equals to 4, it's still nonlinear model, and this kind of nonlinear model is called quartic model in that order. So if b, on the other hand, is less than 1, maybe you have b raised to power half, b raised to power 1 over, b is equals to half, b is equals to 1 over 3, or b is equals to 0.5, b is equals to 0.3, then it's also a nonlinear model, and this kind of nonlinear model is called logarithmic model. So the graph of a nonlinear model, when plotted, is going to be a curve rather than a straight line. So in our next video, we're going to look at how the linear model is estimated. Thank you very much. Once again, don't forget to like, share, and subscribe.